big topic because you use factoring for a lot of other applications. So if you took 065 last semester or any semester, you did a lot of factoring in the sense of like prime factorization. So you factored whole numbers. We're doing exactly the same thing, and we'll use it in exactly the same way. So when you use prime factorization, you used it to find like least common multiples and to find or to simplify fractions and to get common denominators, right, are all the ways that we use prime factorization with numbers. So we'll use the factorization of polynomials in exactly the same way so that we can build fractions out of polynomials, and we have a way of simplifying them and finding common denominators and things like that. We'll also get to use factoring to solve equations that are not linear a little later next week. But the idea of factoring polynomials is really identical to the idea of factoring numbers. It's just, of course, a little bit more complicated because you have to deal with variables and some addition, subtraction. So let's have a look. So first, let's just start with, so this is, I'm just going to call this factoring, but the next like 4 sections are all on factoring. So just as far as vocabulary goes, it's important to understand sort of the difference between like factoring and simplifying, because as we're getting into more complex problems, like there's so many things we can do with polynomials. There's not like a right answer for like a single polynomial, right? It totally depends on what exactly you're trying to do with it, like what you want to do. So sometimes I might ask you to simplify. Sometimes I might ask you to factor because I want to see that you can do all of those things, although none of them are really done usually just for the sake of doing them. So a lot of the things we do in this class are sort of pointless on their own, but we're building all these skills so we can use them within bigger problems in calculus and beyond. So factoring is one of those things, like just like with prime factorization, like you wouldn't write the number 6 as 2 times 3 like just for the heck of it. Like you wouldn't be like, I spent 2 times $3 yesterday, right? Like you factor in order to do other problems. And so the same is true algebraically. It's just we're not going to do every single thing that we can do with this factoring quite yet. So language-wise, if I have like 2 times 3, we know that is equal to 6. So going in this direction is what we refer to as simplifying. So when we talk about simplifying, we're saying do every operation that you can see. So if I give you a big expression and I say simplify this, you will do any multiplication that you see, you'll do any addition that you see, combine everything as much as you can. That's the process of simplifying, is doing operations. When we factor, we're going in this direction. So this is factoring. So you're not actually doing an operation, you're actually undoing an operation, right? Factoring is really just unmultiplying something. So there's lots in between, like when it comes to polynomials. You can have, and we'll see a couple examples later, you can have polynomials that are neither fully simplified nor fully factored. So if you have one of those in-betweens, I could ask you to simplify it, I could ask you to factor it, and so you want to know which direction you're trying to go. And so those are sort of the 2 main words that we'll use to differentiate the 2. So in general, the process of factoring, to factor a polynomial, means to write it as a product of 2 or more polynomials. So we have to be pretty careful when it comes to polynomials because there's a bit more going on than with numbers. So what looks like a product, like how to recognize a product is maybe a little bit more challenging because you can have multiplication within an expression without the entire expression itself being a product. So a couple of examples, like, so 4x squared plus 9x minus 3, there's a polynomial. This is not factored because there is addition and subtraction, right? So if you think of order of operations, like a product is like, it means that multiplication is like the last operation that you would do when simplifying. So here, if I was starting with x, I would have to like multiply by the 4 and multiply by the 9 and then do addition and subtraction, right? So the last operation I would get to, if I was starting with a value for x and simplifying this, the last operation I would get to is addition and subtraction. And so this is not a product, whereas, so this is not a product. Whereas if I have x plus 5 times 9x minus 6, so this is a polynomial in factored form, because if you think about starting with a value for x, if you were going to like put the number 6 in and try and simplify this, the first thing you would do is all the addition, everything inside the parentheses. So the last operation you would do is just multiplication, right? So the main operation going on here is multiplication of like two chunks, right? And there's nothing going on outside of that. And so we say this is factored. And so sort of visually, the easiest way to tell if something is factored or not is there's no addition or subtraction don't mess with me. Outside of the parentheses. Can't fit it. So order of operations wise, those parentheses are saying do all the addition subtraction first, and then you're doing a bunch of multiplication with whatever these objects are that you created with the addition subtraction. So we can think of these factors, like these pieces, as just numbers. So just like with prime factorization, that's like the 5 times the 2 or whatever the prime factors happen to be. And just like there are prime numbers, whose factors are just 1 in themselves, there are also prime polynomials whose factors are just 1 in themselves. So if a polynomial is prime, it means it's completely factored. It can't be factored anymore. And so that's going to be our goal. Just like with whole numbers, our goal is going to be to factor polynomials into the product of prime factors, which won't look like prime numbers because they'll be polynomials, but we refer to them as prime polynomials. So another example that can sometimes be tricky is like x plus 3 times x minus 9 plus x minus 2 times 3x plus 7. So something like this. So this contains some products, right? Like we have x plus 3 times x minus 9, that's a product, and then x minus 2 times 3x plus 7 is also a product, but the entire expression is not a product, right, because it's got that addition in between those two. So this has 2 terms. So terms are things that are added and subtracted, and a lot of, like sometimes it seems like, you know, we have all these like words in math that like, why not just use the same word for everything, right? But like, if you can distinguish between term and factor, it really helps you to kind of wrap your head around what is actually happening in these expressions. So terms are things that are added and subtracted versus factors, which are things that are multiplied. So like we would say that this entire thing, or these 2 entire objects are terms, whereas in the previous example, like these 2 objects are factors. And the reason I'm making such a big deal out of all of this is that when we get to working with fractions especially, it's really important to be able to identify if your numerator and denominator are in factored form or not, because there's all sorts of things we can do with fractions when everything's factored that we can't do if it's not. And so we don't want to start like canceling things, for example, if we're not in factored form. So we have to be able to recognize that when we see it. So let's talk about how to get there. How familiar are you guys with the idea of GCFs? I heard that we put it back into 065. Factoring out GCFs has been in 065 and not in 065, sort of back and forth over the past 15 years, but it's back in now, right? Did you guys factor out GCFs last semester? You did. Okay, so I'll go over it sort of briefly, since maybe you guys have all seen it. What's up?
So the last...
Oh, I'm sorry. Example is not factored.
Oh.
This is not... Saying it's a product and saying it's factored, they mean the same thing. Okay, so the greatest common factor of a set of monomials is just the largest monomial, which is a factor of all of them. So the largest numerical factor and then the most number of variable factors. So when we factor out greatest common factor, we're doing the distributive property backwards. So the distributive property, there we go. The distributive property tells us that A times B plus C is equal to A times B plus A times C, right? We've all seen that a million times in a million textbooks. And we use it all the time to simplify expressions. So going from here to here is simplifying. But we can start on the right side and notice that we have two terms. And that these two terms have a GCF of A. So they both contain a factor of A. When we say they contain a factor of A, what we mean is just that entire term is A times something else. So in this case, the first term is A times B, the second term is A times C. So they both contain a factor of A, which means that we can factor the GCF out. So this is factoring out the GCF. Just means to write the polynomial as your GCF times some other polynomial by undistributing it. So doing the distributive property backwards. So let's do a couple. How about 5x to the fourth minus 20x to the third plus 15x. So when I look for GCFs, I just look at the numerical factors, and then I look for common factors in the variable factors. So 5, 20, and 15 all have a common factor of what?
5x.
Right, so 5, 20, and 15 have a common factor of 5, and then our variable factors have a common factor of x. Good, so our GCF is 5x. And so then in parentheses, we put whatever we would have to multiply 5x by to get our original polynomial. So to get 5x to the fourth, I would need 3 more factors of x. So I would have to multiply 5x by x to the third. The operations between the terms stays the same. To get 20, I would have to multiply 5 by 4. To get x to the third, I would have to multiply x by x squared. Operation stays the same. To get 15, I would have to multiply 5 by 3. And then to get x, I would multiply x by 1. So I don't need any more factors of x. And so we're done. So far, so good? One thing that comes up a lot. It has to do with signs. And we'll be using, factoring out a GCF is really the basis for all the factoring strategies we'll do. And in order for things to work out sort of the way that we need them to, in our other strategies, we have to be a little bit careful about what sign we use for our GCF. So in general, the sign of the GCF that you factor out should be the same the sign of the first term in the original polynomial. So here, the first term in our polynomial was 5x to the fourth, which is positive, and so our GCF was a positive 5x. Whereas if I had say negative 4x plus 24x squared minus 8. So now we have to talk what this word first means, because I could write the same exact polynomial with the terms in a different order, and if we think of first the way that we normally think of first, like the one that comes first, then this polynomial would have a, wait, I have to change something. I'm sorry. This is, I wrote it backwards. There we go. If we think of first in the sense of whatever we see first, then the first term would depend on how I write this polynomial, right? Like in this case, the first term would be 4, but if I were to write it in a different order, then the first term could be 8 or it could be 24x squared. And so we have to think a little bit about what order we're going to put things in. And so we're going to start, let's see. So I'm going to write out our basic, our like complete factoring strategy. If you guys don't want to write this down as I do it, you don't have to. I'm going to give it to you as a handout later on, but we're just going to build on it over the next few days. So I'm just going to like have it here. So I don't want to give it to you until we've like completed it. So our factoring strategy, so the first thing we're going to do is put the polynomial in descending order. And there's nothing wrong with a polynomial that's not in descending order, but this consistency allows us to say things like the first term, and allows us, like, it really just helps with our signs all working out nicely if everything is in a consistent order. So when we get to this example here, we say, okay, that's not in descending order, right? Remember, descending order means that the degrees go from highest to largest, or to smallest. So the largest degree is that negative 24x squared, so that should come first. And then 4x, and then negative 8. And so the first term is the leading term, so the term with the highest degree is what we mean by this. And so I noticed that my first term is negative, and so I have a GCF of 4 here, but because my first term is negative, I'm going to actually take out a negative 4. So we have negative 4, and just like when you distribute a negative sign, this is going to change the sign of all the terms. So I'm going to get a positive 6x squared a negative x, and then a positive 2. Right? So if you're looking at negative 8, you want to think, like, what would I have to multiply negative 4 by to get negative 8? You'd have to multiply by a positive 2, right? If it was a negative 2, that wouldn't give you your negative 8. And to get a positive 4x, you would have to multiply a negative 4 by a negative x. So, like I said, just like when we distribute a negative, factoring out a negative will change the sign of all the terms. Any questions so far? Yeah?
I'm kind of confused when you explain when it says in general the sign of the GCF. The sign, is that just like x?
Like if it's positive or negative? So like in our first example, the first term was a positive 5x to the 4th. And so the GCF we took out was a positive. And then in our second example, our first term was negative 24x to the 2nd. So that was a negative, and so we took out a negative. And like I said, it's not like it's wrong if you don't take out a negative, but it's going to make like the consistency of taking out the sign of the first term is going to make things like common factors actually look like common factors instead of getting things with signs that are backwards. So the way that we're going to use this factoring of GCFs to extend this to factoring all polynomials or factoring polynomials completely is by recognizing that we can have GCFs that aren't necessarily just like numbers or just like single variables. So let's look at this guy. We'll use color coding here. So factor x squared times a plus 2 times a. So how many terms are there in that polynomial? There's 2, right? Remember, terms are separated by addition, subtraction. So I have 1, 2 terms. And what common factor or factors do they have? Yeah, they have a common factor of a, right? And so just like we did before, I'm going to pull my a out to the front. And then from the first term, when I take a factor of a out, I'm left with x squared. And in my second term, when I take a factor of a out, I'm left with a 2. So exactly like what we just did. But the thing is that in math, we can express numbers in lots of different ways. Like x plus 5 is just a number, right? It just happens to be 5 more than whatever number x is. And so numbers that we factor out aren't always going to look like just single numbers, right? So we could do this same exact problem and say x squared times x plus 5 plus 2 times x plus 5. So now how many terms does that polynomial have? Yeah, it still has 2, right? There's still, like any addition or subtraction going on inside parentheses doesn't create a new term. It's just addition, subtraction going on outside parentheses. So we have 1, 2 terms. And then do they have any common factors? So let's think about the multiplication going on within each term. So the first term is x times x gives me my x squared, right? So, and then times x plus 5. So we usually think of that as just 2 factors, a factor of x squared and a factor of x plus 5. And then the second term is 2 times x plus 5. So we have a factor of 2 and a factor of x plus 5. So did they have any factors in common?
X plus 5.
Yeah, so they both have a factor of x plus 5, right? They are both something times x plus 5, which means just like we did with the a above, we can pull the x plus 5 out. And then taking that factor of x plus 5 out of the first term leaves me with a factor of x squared. I have addition between my terms, and taking a factor of x plus 5 out of the second term leaves me with a factor of 2. And if you get it all mixed up about what goes in sort of like the leftovers, right, like the blue set of parentheses, like you can literally take the factor out, like physically, like take a factor of x plus 5 out of both terms, and what you're left with is what goes in your second set of parentheses. So if you are getting it all mixed up about what that should look like actually use your eraser and like erase your factor, and it'll tell you what's left. Any questions? So it looks quite a bit different, but we're really doing exactly the same process here. Just turns out that the factor that we're pulling out is now what we call a common binomial factor. So a binomial is a polynomial with two terms. So we're pulling a common binomial factor of x plus 5 out, just like we've pulled out a factor of a up there and a factor of whatever we pulled out in the previous examples. So let's do... let's do this. So a minus b times x plus 5 plus a minus b times x plus 9. So how many terms do I have? Yeah, still 2. This is a term, this is a term, and do they have any factors in common? A minus b, right? So within each of those terms, we have a product, right? And we have a minus b times x plus 5. Those are the two factors in the first term. And then a minus b and x plus 9 are the two factors in the second term. And so they have a common factor of a minus b. And then this gets a little bit tricky because we have to be careful with parentheses. So everything else has to go in one set of parentheses. So I'm going to have like a big set of parentheses. When I take a factor of a minus b out of the first term, I'm just left with a factor of x plus 5. And then we have addition between the terms. And then when I take a factor of a minus b out of that second term, I'm left with a factor of x plus 9. So really this whole thing is like my second factor. And that can be simplified, right? What's inside those parentheses is really just addition at this point, because there's nothing in front of these sets of parentheses that you would have to distribute. And so this is a minus b times 2x plus 14. And incidentally, that is not fully factored because, I didn't mean for this to happen, but it's kind of exciting that it did. Because notice that within that second factor, I have a common factor of 2. You guys see it? So I can write this guy as 2 times x plus 7. And so our final answer would be 2 times a minus b times x plus 7. So just like when you're doing prime factorization, like if you had the number 20 and you were going to find the prime factorization, you could be like, oh, 20 is 4 times 5. But like that's not a prime factorization, right? Because one of the factors can be factored further. And so you would go on to write this as 2 times 2 times 5. So the same thing is true when working with polynomials. You can factor once, like we did right here. But then we notice that one of our factors can still be factored. And so we continued factoring there. So that second step is just the same as me writing the 4 as 2 times 2 instead of as a 4. Does that make sense?
So is it wrong if you don't factor out like what we did there?
So the concept of wrong and right is a little bit more fluid now than maybe it has been with math in the past, because there's a lot of things that we can do that are mathematically correct that don't actually get us to where we want to go or achieve the purpose that we're trying to achieve. So it is not incorrect in the sense that it's not true. However, if our goal is to factor completely, so just like if you wrote the number 20 as 4 times 5, that's not incorrect. It's true. However, if you're using prime factorization for some purpose, like simplifying fractions or finding an LCM, this is not a prime factorization, right? The prime factorization is 2 times 2 times 5. So it's not incorrect, but it's not a complete factorization. And we'll always go for complete factorizations because having individual factors is how we recognize things like common factors and stuff like that. So I wouldn't ever say it's wrong because it's mathematically valid, but it's not complete. And I'll always use, like on your homework, I always use the the terminology like factor completely so that you guys know, like you got to break it all the way down. But we'll see as we start using these in a couple weeks for rational expressions that we really want to get everything separated so that we can cancel things that are like
A minus B times 2 x plus 7 is the endpoint.
Yeah, so this is a full factorization right here.
Not the.
This is also, those are equivalent. We just, usually we're used to seeing like monomial factors in the front, right? Usually like when you're given a problem and like to distribute, they usually don't write it like this. So it's a little prettier, I guess. But both those last 2 lines are both full factorizations. Okay, so from here, we're going to move into factoring polynomials by grouping, which is, so our first step in factoring any polynomial is always going to be to factor out the GCF. Our second step is going to be to ask ourselves, how many terms are there? Because the number of terms is going to determine the strategy that we use to factor. So if there are 4 terms, we're going to use what we call grouping. So we're going to factor by grouping. And really our factoring strategy is going to be that if there are 3 terms, we're going to write it with 4 terms and then factor by grouping. And if there's 2 terms, we're going to write it with 3 terms and then write that with 4 terms so we can factor by grouping. So that way it's sort of all just like a progression. It's not like different things. Like you don't have to memorize like 7 different ways of factoring. You just sort of build on this general idea. So the idea of grouping is that we can make a polynomial look like this. You won't typically get that as like nobody's going to give you a polynomial that looks like that to begin with, right? We will usually start with polynomials in like fully simplified form. So we have to figure out a way to get from something like that to something like this so that we can apply that same idea. And so that's what grouping does for us. So for example, let's factor (8x to the 3rd) plus 2x squared plus 12x plus 3. So first I put it in descending order, which is already done. And then I ask myself, is there a GCF I can factor out? And in this case, there isn't a GCF other than 1. I mean, everything has a factor of 1. But 8, 2, 12, and 3 don't have any common factors. And then one of my terms doesn't have a variable, so I can't pull an x out. And so then I ask myself, how many terms are there? And how many terms are there? 4, right? So 1 term, 2 terms, 3 terms, 4 terms. And so I'm going to factor by grouping, which means you're going to split your polynomial into 2 groups, the first 2 terms and the second 2 terms. If you want a visual way of doing that, you can use like a little like dash line right here after that second term. Don't use parentheses because you will, most often if you use parentheses, you will turn addition into multiplication. And so it's not what you want it to be. And then we're going to factor the GCF out of each group. So 8x to the 3rd plus 2x squared has a common factor of 2x squared. So we've got 2x squared times 4x plus 1. And we need that factor of 1. So that's why I always like say like when I think about what goes in those parentheses, I think about what do I have to multiply 2x squared by to get what I started with. So to get 8x to the third, you would have to multiply 2x squared by 4x, which gets me this 4x right here. To get 2x squared, you would have to multiply 2x squared by 1. If that 1 isn't there, then it sort of serves as a placeholder for us, because if it wasn't there, right, like multiplying those two things does not give you 8x to the third plus 2x squared, right? We have to have that 1 there. And then the operation between your groups always stays the same. So in this case, it's addition. And then 12x plus 3, those two terms have a common factor of 3. So we'll pull that out, and we get 4x plus 1. And now we are back in the same situation we were in back here, right? We have two terms. So each one of our groups is a single term. And then our two terms have a common binomial factor of 4x plus 1. So I'm going to pull that 4x plus 1 out. And then if I take a factor of 4x plus 1 out of the first term, I'm left with a factor of 2x squared. I have addition between my terms. And then if I take a factor of 4x plus 1 out of the second term, I am left with a factor of 3. And so that is my fully factored polynomial. I mean, we'll check to see if those two factors could be factored anymore, but we'll do that next week. I won't give you any that you can factor further at this point. So let's do some more examples. Does that make sense, that process? So we're really just pulling a GCF out twice. We're pulling the GCF out of the two individual groups and then pulling the GCF out of the whole thing. So let's factor. Oh, did not work out. There we go. Let's do 3x to the third minus 6x squared minus x plus 2. So again, this is already in descending order, and there's no GCF I can take out of the whole thing, right? 3, 6, 1, and 2 don't have any common factors other than 1, and one of my terms does not have a variable, so I can't pull out an x. And so I'm going to split this into my two groups. And that first group, I have a common factor of 3x squared. So I get 3x squared times, I need an x in my first term and a 2 in my second term. And then the operation in between never changes, so this is a minus. And then x and 2 don't have any common factors other than 1. And although when we're pulling out GCFs of the whole thing, we don't normally pull out 1s, in this case, it's convenient to pull out the 1 so that like you have something in this position when you do the next step. Otherwise, you can sort of end up with like nothing here when you factor out your binomial factor, which ends up getting a little bit messy. So so what we're really factoring out, go ahead.
Are you always going to be able to just split it right down the middle? Or
Yes.
Okay.
As long as it's in descending order, then doing 2 and 2 will get you where you're trying to go. There are some more complex polynomials that have like 5 terms where you can like split it into like 2 and 3 if you have like a perfect square, but we won't get into those for now. So what I'm really factoring out here is a negative 1. So taking a negative 1 out of negative x gives me a positive x, and taking a negative 1 out of a positive 2 gives me a negative 2. Be really careful with your signs there, because if you mix up your signs, then your binomials won't be the same. So now we have our two terms, one term, two terms. They have a common binomial factor of x minus 2. And then my leftovers are 3x squared minus 1. It should be noted that, I think I have time to do an example of this, but that if you don't have a common binomial factor in this step, like you can't factor, right? All of this is based on the fact that we're taking that x minus 2 out of both terms. If that x minus 2 isn't the same, if one's x minus 2, one's x plus 2, then you don't have a common factor that you can pull out. So for example, like x to the fourth minus 2x to the third minus 5x minus 10. Descending order, no common factor. So if I split this, I can take x to the third out of my first group and get x minus 2. And then I have subtraction between my groups and a common factor of 5. So I'm really factoring a negative 5 out. So you take a negative 5 out of negative 5x, you get a positive x. And when you take a negative 5 out of negative 10, you get a positive 2. And I don't have a common factor here, right? I have two terms. They don't have any factors in common, right? The first term has a factor of x to the third and a factor of x minus 2. The second term has a factor of 5 and a factor of x plus 2. There is nothing common there that I can pull out. And this, remember that this step right here is not factored, right? Because of that subtraction in between. And so if you get to this point and you don't have a common binomial factor, we just say it cannot be factored. And, I mean, technically we say it cannot be factored by grouping because there are some ways to factor four-term polynomials that aren't grouping, but we won't do any of them, so you can just say it can't be factored, or that it's prime, which means that it's a polynomial that can't be factored. So be careful not, one of the biggest mistakes that people make with factoring is trying to force things to happen by fudging a little bit. So like it's really easy to try to like look at what we just did and like when you get to that second piece be like, oh, that should be a negative 2 because you really want it to be a negative 2 for all of this to work. But mathematically it just isn't a negative 2, right? Because negative 5 times negative 2 is not negative 10. So just try not to fall into that trap of trying to force things to work if they don't actually work. In particular, signs are things that we like to really try to manhandle into working the way we want them to, but then they just don't. So your homework tonight will be